between 4 values. It's cyclic. We call this like cycle, cyclic. All right. We'll need that in a second. All right, so e to the x. Remember the Maclaurin series for e to the x was 1 plus x, x plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial plus x to the 5th over 5 factorial, et cetera, right? Yes. But what I'm going to try and plug into this instead of x is I times pi. So replace all your x's in here with I times pi. And let's just see what happens. You ready? All right, this is equal to 1 plus what? I pi. With me? All right, x squared would be I squared x squared over 2 factorial. Agreed?
Where's the pi at?
Pi, yeah, I forgot the pi. Sorry about that. How about I do it like this? I pi squared x squared. Is that right?
I thought you were plugging in.
Sorry, my mistake. Cubed, I cubed, pi cubed over 3 factorial. Keep going. Plus I to the 4th, pi to the 4th over 4 factorial. I'm going to go more. I'm about to refer to this red table here in a second, though. I to the 5th, pi to the 5th, 5 factorial. I to the 6th, pi to the 6th, 6 factorial. I to the 7th, pi to the 7th, 7 factorial. Maybe 2 more. I to the 8th, pi to the 8th, 8 factorial. I to the 9th, pi to the 9th, 9 factorial plus dot, 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 dot. Now that looks terrible, but let's just discuss these i's. What is this one right here? -1, right? Mm-hmm. What is I cubed? Negative I, right? What is I to the 4th? 1. Okay. Now I start repeating, right? And what was this one? This one was just I, right? The number in front of pi? Right here? Okay. This next one right here should be then what? I, and then this one, -1, then this one, negative I, and then 1, and then I, and so on and so forth, right? All right, we're getting there. So that is equal to 1 plus I pi. What, minus? What? I squared is the minus.
Minus pi.
Pi squared over
2
factorial. The next one? Minus I pi cubed over 3 factorial plus 1 pi to the 4th over 4 factorial. Yes? Plus I pi to the 5th over 5 factorial plus or minus? Minus pi to the 6th over 6 factorial minus I pi to the 7th over 7 factorial plus 1 pi to the 8th over 8 factorial plus I pi to the 9th over 9 factorial. We agree? Dot, 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 dot. Yeah. Okay. This is cool. Y'all still on board?
Yeah.
All right. I'm going to underline everything that does not have a pi. an I. Okay? And I'm going to just write those next to each other. This would be 1 minus pi squared over 2 factorial plus pi to the 4th over 4 factorial, what? Minus pi to the 6th over 6 factorial plus pi to the 8th over 8 factorial, right?
Mm-hmm.
What would the next one be?
Minus 2.
Minus pi to the 10th over 10 factorial. So I'm just going to put here plus dot, 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 dot. Agreed? Okay, it's that, whatever this is, plus, now I'm going to take everything that I did not underline in green, which all of the things here in red all have a what in them? An I. If they all have an I can factor an I out, can't I? I can factor an I out. So I'm going to factor an I out of every one of those red ones, and then tell me what you have in there.
Pi.
You have what? Pi
Minus 3.
minus
Pi cubed over 3.
pi cubed over 3 factorial plus pi to the 5th over 5 factorial minus pi to the 7th over 7 factorial plus pi to the 9th over 9 factorial. You agree?
I agree.
Plus dot, dot, dot. Yes? Does this look familiar?
Looks like
I heard someone say all evens, right? Okay, so if you go and you look at what I wrote down a second ago, I said cosine looks like this. 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus x to the 8th over 8 factorial. I said that was cosine x, right?
Yes.
But if you look, if you replace all these x's with pi's, isn't that this? Yes? Do y'all see that?
Cosine of pi is
So this right here, all of this is just cosine of pi plus I times, now do you recognize this? Sine of pi. That's sine of pi, isn't it?
Yep.
Sine of pi. And what is sine of pi? 0, so that's gone. What's cosine of pi?
1.
Negative 1.
Negative 1.
I'm done. Isn't that what I had to show you?
Yeah,
Right?
1 plus 1 equals 0.
This is equal to
Negative 1.
-1 plus, this is all 0, which is -1. So what I showed you was that e to the I pi was equal to -1, which means if you add to both sides, add 1 to both sides, you get the equation.
That's cool.
Yeah. Understand?
Yeah, that's intense.
Yeah, that's pretty cool, right?
That makes so much more sense now. But you kept showing this like little bits and pieces of this in college algebra and Cal 1. Now
Yeah, now you finally get to see it.
that's cool.
All right. Let's, yeah, no, you wish. All right, so let's do a Taylor series, okay? Let's do a Taylor series, and let's just see that these can get a little bit ugly.
Great.
The final is on Tuesday, I believe. I believe it is. I have to check, but I believe it is next Tuesday. A week from today. Check, well, hold on, I have the calendar right here, I think. Tuesday, 11 a.m. Yep, 11 till 1:45. That's the, yeah. Okay, I want us to find the Taylor series for f of x equals the natural log of x at a equals 1. All right, this is going to be a little messy, so just be prepared. All right? Let me write down, first of all, what the Taylor series is so we don't confuse it with Maclaurin. The difference between the Taylor and Maclaurin is that I'm going to have to find a sum n equals 0 to infinity. I'm going to have to do the nth derivative, but instead of at 0, it's going to be at a over n factorial and then x minus a to the n. So the big difference is that that's an a instead of a 0, and that's an a instead of a 0. For this specific problem, they actually want me to let the a be what? 1. So I need to find the nth derivative at 1 over n factorial x minus 1 to the n. All right, so this right here is specific to this particular a, right? If they gave you a different a, then you would change that to, whatever it was, right? 2, 2, whatever, -5, doesn't matter. I'm going to need to take successive derivatives of natural log in order to make this happen so that I can try and come up with a formula for this. Because I don't know what the nth derivative at 1 is. When it was e to the x, it was easy, right? But for this, it's not. So I'm going to do a table and look at all these derivatives of natural log. I'll try this again. I'll put my n's here, my nth derivatives, and then my nth derivatives at 1, right? So there's a difference between this column and this column. This column, I'm just taking the derivative over and over and over. Here, I get to plug 1 into those once I'm done. So let's start with n is 0. When n is 0, what's the 0th derivative? Which is natural log x. And what's natural log of 1?
1 over x.
Natural log of 1?
Oh, 0?
0. I hate to do the table here, but I'm going to just, okay, that's what I'm doing. Understand? All right, let's let n be 1. What is the first derivative of natural log of x? 1 over x. I don't want to have to do this, but damn it, I'm going to. The derivative of natural log of x is 1 over x. And what happens when you plug in 1 to this? So you get 1 over 1, which is 1. Agreed? All right, let's take the derivative of this. Now, I'm going to rewrite 1 over x as x to the negative 1 because it'll be a little easier for me to take the derivative of x to the negative 1. So when n is 2, I'm taking the derivative again, and I get negative x to the negative 2, which is really the same as negative 1 over x squared, right? And when I plug 1 into that, I get negative 1, right? Agreed? All right, next one. It looks like maybe it's going to switch back and forth between negative 1 and 1 right now, but it's not. Okay, when I plug in 3, okay, take the derivative, what comes out here? You get negative, that's positive 2 x to the negative 3, which is really 2 over x to the third, right? And when I plug 1 into that, what do I get? 2. Right? 2. And I go again. Fourth derivative. The thing is, we can stop once we see a pattern. Right now, I don't see a pattern yet. It's 0, then it's 1, then negative 1, then 2. What's the next one going to be? Negative 6?
Yeah.
Negative 6, because you're going to come out with this like this? Yep. I agree it's negative 6. But I'm going to look at it a little bit different because I can, well, because I've done these before. Okay, so look. Negative 2 times 3 over x to the fourth. I'm going to leave it as negative 2 times 3. Because it's looking like every single time I take a derivative, I'm getting another number out here, right? And it keeps growing. And these are starting to look like factorials, aren't they? All right, so plug 1 into that. What do you get? Negative 2 times 3? which is, I agree, negative 6. But I'm going to keep it here so I can see it clearly. I'm going to stop using red. Fifth derivative, what happens? Comes out, you're going to have a positive this time, right? 2 times 3 times 4x to the negative 5, which is 2 times 3 times 4 over x to the 5th, which is just 2 times 3 times 4, which of course we can figure out what that is, right? So it looks like these are factorials, right? These are factorials. Is it exactly what's over there, though? Look like this is 2, right? Is that 3 factorial? No, this is what? 3 factorial? But that's when we're at 4. And then here it's what? 4 factorial when we're at 5. So it looks like this is an n minus 1 factorial, doesn't it? But it's also switching signs.
So negative 1.
But does that work going backwards?
Yeah.
This is 1 factorial. Well, forget the negative. That's 1 factorial. That's 0 factorial. That's a problem. Do you see that? We can't go negative on the n. So I'm already kind of figuring that this right here might be an issue for me. So I got a question mark just next to that one. But I'm thinking this one, in terms of just the numbers, this looks like a 0 factorial, this looks like a 1 factorial, this looks like a 2 factorial, this looks like a 3 factorial, this looks like a 4 factorial, with changing signs happening, right? And this one up here, I don't know. Understand what I'm doing? Okay, so now I come back over here. Let me do one more. I think one more should be enough. 6, so we should get negative 2 times 3 times 4 times 5, x to the negative 6, and that should give me negative 2 times 3 times 4 times 5 over 1, so this should be a 5 factorial. So the question becomes, if I were to plug in over here, there's more to this table, right? But if I got down to the nth one, forget this. What's the pattern we have over here?
2 times 3 times 4.
This is, it's always 1 less here, factorial, right? So this is n minus 1 factorial, but it's switching signs. And when I plug in, remember we can't start with the first row because it doesn't follow the pattern. When we plug in 1, we get what? Positive. When we plug in 2, we get negative, then positive for 3 and negative for 4. How can you create an alternating thing? Negative 1 to the n, will that work?
We start at 0, right?
If we start n at,
Plus
well, what happens if I plug in 1? What will happen if I plug in 1 here?
negative 1, so it's plus 1.
I will get a positive. I don't want that, do I? So plus 1?
Yeah. However you're trying to see.
Do y'all agree with this?
Yes.
Understand it? No questions? Good. So here's what I've got. So far, I can say this about C sub n. Right? C sub n, which by definition, I'm going to put it up here just so you can see it again. That's C sub n, right? That's what I'm trying to figure out a formula for. I know that that's equal to, I know this up here, right? This up here should follow this pattern right here, right? It should be negative 1 to the n plus 1, n minus 1 factorial over n factorial. Yes? That should work. But that only works when n is what?
Starts at 1.
1 and on. For n greater than or equal to 1. That's the only way that that formula works. Questions? Yes? Because remember at 0, if I try and plug 0 into this formula right here, that should give me my first answer of 0 here. If I plug 0 into this, I get negative 1 factorial, which doesn't make any sense. So my formula is good only after that first step. All right, here we go.
Are you not including the x minus minus 1 to the n because x is 1.
This is C sub n. This is the thing in front of it. Remember how I wrote power series C sub n x minus a to the n? And we said, oh, this is all we're worried about? Now I'm going to go back and write the power series. Okay? So here's what I've got. I know that the natural log of x about a equals 1 should be equal to, I'm going to leave a space here on purpose, sum n equals 1 to infinity of this formula, negative 1 to the n plus 1 over n factorial. No, I forgot that other piece. N minus 1 factorial x minus 1 to the n. Right? That's what it is. But I have not accounted for that first piece. But what was the first piece?
0.
It was a 0, right? So I know that in front of this, I have, what, this piece up here? I should say this piece up here. The 0th derivative at 1 over 0 factorial x to the 0. That's the very first piece of the Taylor series. X minus 1, sorry, to the 0. That first one, I know that that's a 0, which kills everything off. So there's a 0 in front of this, so I don't need it. Do you understand that? But if the problem was different, and you were asked to do natural log of x at 2 instead of 1, then that first piece would no longer be 0, because the only reason it was 0 is because it was natural log of 1. Okay? If it was natural log of 2, then that first piece would be natural log of 2 over 0 factorial x minus 1 to the 0. So it would just be natural log of 2.
Okay.
There's an example like that in the homework, okay? All right, so that's, since I don't need that, there it is. Now I need to clean that up because there's a little bit of simplification I can do. Do you see what I can do? The n factorials can be simplified a little bit. I can actually peel off this one. I can peel off this one an n and write it that way, and then cancel like that, right? And so I get the natural log of x is the sum n equals 1 to infinity of negative 1 to the n plus 1 over n, x minus 1 to the n. That's what I would get. Questions?
Isn't x always 1 though? And so that would always be 0.
No, x is not 1. We are, what we're doing is we're moving, remember that a power series is a function, right? What we're doing by saying minus 1 is we're shifting the function left or right. That's all we're doing.
Gotcha.
Questions? This is the power series. Now, we could write out the first few of these if we wanted to. Like, let's let n be 1. If n is 1, we would get what? If n is 1, we get.
Negative x minus 1.
Just get x minus 1 to the first power. You got a question? What's up? No? You sure?
Just saying, like, the ln can never be 0, so you have to start at 1. So never, like, actually, it never goes to 0, so it almost makes sense. You have to start at n equals 1. That's what I was asking. That's what I was thinking.
You could not let x be 0 here.
Yeah, exactly.
Yes, that's right. Let's do something. Let me finish this. I'm just writing out what it is, okay? So if I plug in 1, I get that. What happens if I plug in 2? This will become negative? Negative 1/2 x minus 1 squared. Next one, plus 1/3 x minus 1 cubed. Minus, and then it would continue, right? This, whatever. That's the power series expansion, or that's the Taylor series of natural log of x about a is negative 1. All right, I've got to try something real quick. What is I for this? So do a quick ratio on this. Limit n goes to infinity. I'll go kind of quick through it. Do I need to even look at this? No? So I'm going to have something like this. It'll be like x minus 1 to the n plus 1 over n plus 1 times that flipped. So n over x minus 1 to the n. I need that less than 1.
Those x minus 1. One of them.
This and this go away. All you're left with is x minus 1. Agreed? And then you have the n's in here. So limit n goes to infinity, n over n plus 1 times x minus 1. I need that less than 1. Take the limit as n goes to infinity, infinity over infinity. L'Hopital one time, you get 1. And so here's where we are. We have that the absolute value of x minus 1 is less than 1, which means that x minus 1 must be less than 1 but greater than negative 1, which means that 0 is less than x is less than 2, right? Adding 1 to both sides. And you would still need to check the endpoints, right? You would have to check the endpoints. You'd have to let x be 0. What would happen if x was 0? What do you think would happen if x is 0 here? Well, do you all follow what I've done? I found the powers. I found the Taylor series for natural log of x, shifted about a equals 1. I found that the interval of convergence was this interval. So remember, this is why I said, hold on a second. Because you were saying, well, you can't plug in 0. I agree. I think it's going to be divergent there, right? I have to check, though. But it makes sense you shouldn't be able to do it because natural log of 0 should be undefined. But how about 2? Should I be able to plug in 2? Yes. Maybe. So now what I would do is check the endpoints. I'm going to do this, all right? I've come this far. There's no need to stop. All right. So how about the endpoints? Endpoints. So what if x is 0? Let's try that. So go into your formula right here, which this was not the most cleaned up version. The most cleaned up version was this one right here. Right? That's the most cleaned up version. Let x be 0, and what does that turn into? Sum n equals 1 to infinity, negative 1 to the n plus 1. Then this is going to turn into what? Negative 1 to the n. I'll put it up here like this, all over n. And if you have the same base, you can add these powers together, can't you? So what is that? Sum n equals 1 to infinity of negative 1 to the 2n plus 1. Agreed? Over n. Ooh, I don't like this. Oh, no, it's okay. Never mind. It's okay. This is the same as negative 1 to the 2n times negative 1. Isn't that the same? And what's negative 1 to the 2n? 1, right? Look, that's an even number no matter what. That's an even number?
Yes.
So negative 1 to an even number is just 1. So this really turns into negative 1 over n. If you pull the negative 1 out, negative 1 sum 1 over n. I'm getting sloppy with my notation here.
Pretty far down there.
What's that?
Harmonic.
Harmonic divergent. Okay, so I'm done. Understand? So it diverges, so I don't include that endpoint. What if x is 0? I mean, sorry, not 0. What if x is 2? Then that sum becomes sum negative 1 to the n plus 1. What? 1 to the n is just 1. So this is over n. And that is different than this, right? That's going to be an alternating series. Because you can rewrite this is negative 1 to the n times negative 1, right? That's what that is. Pull a negative 1 out. That's an alternating series, and you could do the alternating series test on it, and it would converge. So this would converge by the alternating series test. So the interval of convergence would be this.
In the test, you want us to do it like that, or you want to do the other one?
Either way. You could do the bracket in parentheses. That was a little bit more challenging.
That's cool.
Okay.
Is this the last section?
This is the last section we're going to do. There's still more that we have to do next class in this section. But I still have 10 minutes. So. All right.
Professor, why is the interval of convergence only up to 2? Like if you can plug in any number after 2, or any number after 0?
That power series that we have is only good up to 2. If you go past 2, that power series won't converge, and so it no longer approximates, it no longer is the natural log function. I don't know, okay, what we have to kind of back up and talk about what we've done here. We all know this is natural log of x, right? All right, what we did is we said, look about x equals, a equals 1. And if I let a be 1, then I can approximate this with this power series. And this, remember the pictures I showed you way back in the beginning of this chapter where I said, does that look good? No. Does this one look better? Does this one look better? What we can do is there's some polynomial function that approximates that, right? And this approximation is only valid between 0 and 2. That approximation is only valid in here. So then you're like, well, I know you're saying to yourself, but you know, I could plug in 5 and get natural log of 5. Yes, I agree, and my approximation wouldn't work. So what I would do is I would change this to 5, and that would shift my approximation over, and now I would have an approximation that worked. Does that make sense? Okay. Now with sine of x and e to the x and cosine of x, you don't have to worry about that because the interval is everything. You would not be able to do Maclaurin series for ln x. That's right. You would have to shift it. And the reason is because if you try and go at 0, then it's going to have a radius of convergence and it'll take you into the negatives, which you can't have. So you're always going to have some positive shift in order to approximate. All right, well, this, like I said, was impossible to integrate, but we have a way of rewriting e to the x squared. And we just did this a second ago when I did the e to the ix and I proved that thing, right? All I have to do is plug into the Maclaurin series for this. It was 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the 4th over 4 factorial. Wasn't this the formula for e to the whatever? So if I just replace all of these things with x squareds, do you see that that's the power series expansion of e to the x squared? And then this would become 1 plus x squared plus, let's see, x squared is x to the 4th. 2 factorial is 2, so 1/2 x to the 4th, right? Next one would be plus 1/6 because 3 factorial is 6, x to the 6th plus, let's see, what's 4 factorial? 4 times 3 times 2 is 24, and then x to the
6,
eighth. And then I could keep going, right? I'll do one more. 1 over 1, 7. Hold on, I've just lost my 7. I'm at 5 factorial, 120, right? I don't know why I just had a complete brain fart. What would the next one be, though? X squared to the 5th, so x to the 10th. Understand? And so if someone wanted me to integrate this, I would not be able to find a nice closed answer for you. Like if someone asked you, what's the antiderivative of cosine x? Everyone would say, sine x plus c, right? Sure, you have a function that is its antiderivative. Here I can't, but here's what I can do. I can make this the same as this question. And then integrate term by term. So the antiderivative of that would be, let's do it. What is the antiderivative of that? X, 1/3 x cubed, 1/8 x to the 5th. No, 1/10 x to the 5th plus 7, 1 over 42 x to the 7th plus, and dot, 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 right? And so you might say, well, wait a minute, this is an approximation of e to the x squared, and I would agree with you, because we can't go forever, right? And so the antiderivative would be an approximation also, because I can't go forever. But if someone actually put like limits of integration up in here, 0 to 1, right? If they did, then I would be evaluating this from 0 to 1, wouldn't I?
Yes.
The antiderivative. And if I plug 1 into this, I'm just going to get 1 plus 1/3 plus 1/10 plus 1/42 plus dot, 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 dot. And when I plug in, subtract from it, when I plug in 0, what would I get? 0, that wouldn't matter. And the question now becomes, does this converge? And so we could come up and we could determine it converges. But more importantly, if you're building an aircraft wing, you only need this within a certain tolerance, right? You only need that integral value to a certain degree of precision, I guess. So it doesn't matter at the end of the day. It's better than just looking at it and going, I have no idea how to integrate that. I don't know what to do. And that's the difference between the two fathers of calculus. You had two men who created calculus independently of each other, different parts of the world. Newton and Leibniz were the two fathers of calculus. And the big difference between them is Newton had power series, and Leibniz didn't come up with the power series. So there were things that Leibniz could not integrate that Newton did have a grasp on, that he could do something with it. So that's why I've always preferred Newton over Leibniz, although Leibniz notation is actually pretty nice. So, all right, we have a couple of minutes.
You studied like both of them though?
We didn't really study them, no.
No, like Leibniz, or do we always just focus on Newton? Like, have I ever seen, Leibniz?
You've seen Leibniz notation. When you saw, the derivative, you can look at the derivative like y prime, and you could also write that dy dx. Like Newton wrote this prime notation, and Leibniz used that notation.
Okay.
See, because they both knew the idea was the derivative, right? But they both had different symbols for what it was.
Oh, gotcha.
But Leibniz actually makes certain things look more natural. Like when we did like dy dx and multiply both sides by dx, like that sort of thing, that seemed to make a little more sense.
Mm-hmm.
So there are some times when we prefer his notation.
Gotcha.
All right, so what I would encourage you to do is get started on this homework. Theoretically, you can do everything except the problems 55 through 58. There's nothing new in terms of the formulas. You've got everything you need to do the problems I put on the board at the beginning of class. What did I tell you? 5 through 18?
Yes.
Page 487. You can do all those. I've done them on video. Get working on those, see how it goes. And then we will come back, our last class, our last meeting. I know, no tears, please. Okay? On Thursday, we will talk about how you divide and how you multiply power series. So think about this for a second. I know you can start packing up, but I want you to think about the following. If you were asked to take, I'll make this real simple for us. 1 plus x squared plus x cubed plus forever. Okay, that's an infinite series, right? That's a power series. What if I asked you to multiply that times 1 minus x plus x squared plus minus x cubed plus x to the 4th, dot, 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 forever. So how would you do that? It's like an infinite FOIL, isn't it? Because you have to start with 1 times all of those, plus x times all of those, x squared times all of those, and you keep going forever, right? And even though we can't actually get an answer, we can look at what the first few terms might look like, right? And then, more profound question, and I hate this symbol, but what happens if you take that and divide it by that? Long division? Long division. Yeah, it's the longest long division you've ever done in your life. So we are going to do those two operations. All right, we're going to make sure you know how to do these. All right? And that'll be it. What's on the final? Yeah, I'm going to sit down and I'm going to take a look at everything, pull up some of my old finals, get an idea of what I asked, and we will talk about that on Thursday. I'm thinking I'm going to spend the first hour on this stuff, and then after that we can discuss final. I might introduce polar coordinates to you, not to test you on it, but just to show you it, but it'll just depend on how things go. There's only so much I can tell you. Do your homework, right? Study. It's going to be from, where are we going to, most of the focus is going to be chapter 8. I mean, we had a test up through what, 8.1 or 8.2, right? So most of the final is going to be driven by chapter 8, but there will be some basic stuff from, solid, revolve maybe something. I don't know. Let's talk about it Thursday.
Are you going to ask us to write calculus through this?
I don't know.
As a bonus?
Maybe.
I know that was a bonus.
It was a bonus?